Full screen now.
Okay, let's start our seminar, please.
Okay. So thank you and hello everyone. Very glad to see you all and thank you for invitation. I am Alex Razim, in case you don't know, a student of Vadim Grigorьевич Kaidash like 10 years ago and currently a postdoc fellow in Ruđer Bошковіча Institute in Zagreb, Croatia. And I'm going to tell you about one of my projects related to the LSST synthetic magnitudes. But since I do not know how familiar you are with LSST in general, I assume that you heard about it a lot. But still, I would like to make a short intro, considering that LSST is about to start operations. Well, actually, it already started operations. It got first light several weeks ago. And we are expecting the first data preview release maybe in 6 or 7 months in summer 2025. So I would expect that you will hear a lot about it in the future, and I would like to make a short intro about what it is, about what it's going to do, and why are we so excited about this? Those of us who are excited, obviously. So it is another very big telescope being built in Chile with a geometric diameter of window around 8.4 meters. And this is called, well, people who are advertising it in the broad community are usually calling it a telescope for observing the universe in real time, like making a movie of the whole universe. And the reason for this is that LSST, or Vera Rubin Observatory to be precise, because LSST is the name of the first survey that is going to be conveyed on this observatory. So Vera Rubin Observatory is perfect for rapid and deep observations of large portions of skies. So it will observe almost all south sky, and it has pretty large attitude, so it has a large field of view, good resolution, good depth. It's 24.7 magnitude deep in the air band for a single visit. And the benefit of this telescope is that big field of view and rapid observations make it very good in terms of attitude. So essentially, it will be observing almost whole, on average, almost whole of the south sky every 3 nights. So every 3 nights, 6 bands, it will be observing the whole south sky. Now, in real, the real case scenario, it is not precisely like this because there are a matter of cadences. So essentially the observational schedules, which are constantly changing even now at the stage of simulations and will be changing in the first couple of years of the observations because, well, obviously everyone wants to optimize the observations for their own science, but what is good for observing galactic plane isn't so good for observing extragalactic stuff. What is good for observing rapid variable objects isn't so good for observing long-term variations of AGNs, for example. So obviously there are constantly tweaks here and there about how we are going to observe this field and that field and how we are going to schedule observations in different bands. But on average, we would observe the whole available area once every 3 nights. And for many fields, there will be thousands of observations of the same field, which is very good for precise classification of variable objects. So obviously, this telescope is great for observing changing stuff. In terms of depth, this is how SDSS would see a piece of sky, and this is how LSST will see it. So a lot more objects are going to be observed. And in terms of numbers, we are going to observe about 20 billions of galaxies and about 17 billions of resolved stars. And another thing where LSST is going to be excellent is solar system, because we are expecting to get, in some cases, for some types of objects, almost complete census of them. And another cool thing is that while there will be a yearly data releases as usual, LSST will also produce alerts, so-called alerts, which are going to be rapid notifications of anything unusual that is changing in the sky. So moving objects, so transient events, supernova explosions, tidal disruption events, AGN changes, variability of stars, especially stochastic ones. All of this will be detected in real time with very little latency of only about several minutes. And these alerts will be made public immediately. So all the follow-up observation facilities and all the scientists who want to do science like in real time, maybe detect something unusual, it will be possible. And unlike data releases, yearly data releases that will be made public only after 2 years of proprietary period, these alerts are going to be available in real time. So it seems like there will be a lot of new infrastructure around this observatory, and we would expect an explosion of research related to variable sky. Now, there are 4 main directions in which LSST is going to be making a lot of studies. This is solar system, Milky Way, transient and variable skies, and cosmology. Well, cosmology, because obviously nothing is going anywhere without cosmology these days. So the usual pitch phrase is we are going to detect stuff that will help us understand dark matter and dark energy. But LSST is really excellent for, let's say, more or less near Earth stuff. I mean, as far as Milky Way goes, this near. So I think that this auditorium probably can tell me more about how this kind of survey is going to be useful for studying asteroids better than I can do this. But still, yes, we are going to detect millions of main belt asteroids. We are going to detect about 90% of potentially hazardous objects near Earth. We are going to detect thousands of trans-Neptunian objects, and actually several of higher-ups of the LSST are very excited about this item because, well, I heard that, okay, we're starting the operations of the telescope, I am resigning my position, and I'm moving to look for Planet 9 and get my Nobel Prize, because actually it is expected that the data that will be gotten from LSST will be really good at catching this one horse that no one sees, but everyone expects to find. But something that is particularly exciting, in my opinion, is the prognosis about interstellar interlopers, because it is expected that we will be seeing maybe between 10 and 20 of them every year. And I heard a very curious talk about the possibility that modern space rockets, so like Ariane, European one, or SpaceX stuff, actually, there is a technological possibility to prepare those rockets, the spaceships, in advance, to put them kind of in a waiting mode, and then to observe the sky for the interstellar interlopers, detect them in time to launch the manned mission to intercept these kinds of objects, and to actually analyze them like for real, physically, with people there. Now, it is a bit optimistic, especially considering the current situation everywhere. But I think that it would be really cool. It would be like science fiction, the meeting, the drama from, I think it was Arthur, I think it was Clarke's book. But anyways, so it's probably not going to happen during the LSST period, so in the next 10 years. But Rubin Observatory hopefully isn't going anywhere, so maybe in the next 20 years, we are going to have this mission, and it's probably going to be very cool for all kinds of studying the stellar formation system and interstellar medium. So yes, there are a lot of great things that LSST will do for the solar system, and for Milky Way, it's going to be equally exciting because if, for example, SDSS, which is one of the most successful synoptic surveys that moved the study of Milky Way really far away, so SDSS observed more or less reliably distances only up to maybe 10 kiloparsec, maybe 12. And observe only a quarter of the sky, while LSST will observe half of the sky and to the depths of 100 kiloparsec, or maybe if in some fields even to several hundreds of kiloparsecs. meaning that we are going to have a multi-band precise photometry that will get us good, precise classification of different sources of different stars, that we are going to determine stellar parameters, that we are going to determine distances and in general map the Milky Way with very good precision. In this regard, LSST is quite often called to be the counterpart, the far counterpart of Gaia, because if Gaia was excellent for precise astrometric mapping of our neighborhood in the Milky Way, then LSST will be not as precise, but still pretty good in mapping the Milky Way with photometric distances to the edges of the halo, essentially. Meaning that we are going to trace merger events, that we are going to detect substructures, and this is all kind of has all kinds of interesting applications in terms of detecting maybe even dark matter substructures with stellar streams, with stellar wakes. It is a bit on the edge, so it's a question whether we will have enough precision to do this kind of science. But in any case, we will see the maps of Milky Way being much more detailed in the next several years. Finally, for the transient and variable sky, we will be able to study essentially all kinds of variable objects, starting with things that are changing around us. So faint stellar objects variability, such as brown dwarfs, collisions of asteroids that are currently observed only for the brightest ones. Well, LSST will be able to detect them to a much higher faintness, if I can say so. And extragalactic stuff, of course, because, for example, for tidal disruptions events that are currently, there is only a few dozens of them known. We are expected to see hundreds of them in a single year. So by the end of the 10 years period, we will have thousands of them, or dozens of thousands. Supernova people are not particularly happy about the cadences because they need a bit different stuff, but still LSST is going to observe such high volumes of supernovae that the classification will go to another level, especially with the follow-up observations that will be triggered by the alert that will going to be released in the real time. So we expect that the distance ladder is going to be much more precise, meaning that we will be able to test different cosmological models with better precision. And the detection of new rare, previously unseen objects is also something that we are expecting. So essentially, I already talked about the cosmological, well, something that is much more, that is mostly understandable to me in terms of cosmology, which is related to the transient events, although, of course, the static measurements will be used for galaxy power spectrum and for weak lensing studies as well. So for cosmology, it is going to be useful as well, especially in with joint analysis with Roman telescope that is going to be launched soon. Now, what specifically I am doing? So I'm mostly doing technical stuff, and technical stuff in terms that officially I'm an in-kind contributor to the LSST consortium, which is a bit convoluted to explain because it is administrative stuff, but long story short, since LSST is an American project, European countries by default don't have the data rights. So this proprietary period of 2 years after each data release, European countries by default do not have the right for this data and do not have access to this data. But since the management of LSST has a lot of European people, and actually astronomers are totally fine with sharing this data, that was the funding agency demand to have this proprietary period. There was this scheme conceived that many of European countries are contributing work efforts of their fellows. And this work effort is sort of the payment for the data rights, even in the proprietary period. So those fellow efforts are called in-kind contributions, and I am one of those in-kind contributors for Croatia. So there are several projects that were done within this scheme, but one that is most scientifically interesting is developing a catalog of synthetic magnitudes, synthetic photometry in LSST photometric system using low-resolution Gaia spectra, so-called Gaia XP spectra. So this project is interesting for us because some of my colleagues are working on improving the methodology for photogeometric distances that will be crucial for mapping Milky Way with LSST. So the idea of photogeometric distances, I believe once again that I don't really need to explain what it is, but just in case. So we cannot measure the parallaxes with high precision with LSST because obviously it's a terrestrial telescope and looking as far as hundreds of kiloparsec. Well, usual classical geometric parallaxes won't be really precise for these distances. But the idea is that if we have multi-band photometry and if we have multi-band colors, we can determine the precise location on the Hertzsprung-Russell diagram for the stars. And with multi-band photometry, so if we had only one or two colors, we would have a number of degeneracies. So it would be hard to discern between white dwarfs, main sequence, and some types of giants, for example. But if we have multiple colors, we can make a precise location. We can identify to which part of the diagram the star belongs. And with this, we can determine the luminosity. And with this, with absolute luminosity, obviously, we can determine the distance. It is not as precise as classical geometric parallaxes, but using Bayesian techniques, probability, estimating the probability of the star to be located here and there, the precision is good enough to make quite good maps of the Milky Way. So this is what my colleagues are working on. And what I am working on, since we don't have the LSST photometry yet, is I am working on producing the synthetic magnitudes that can be used for testing this framework and for testing the methodology. And in the future, these magnitudes will be also good for calibrating the photogeometric distances against Gaia geometric parallaxes, and even using these datasets as a joint. So essentially with this calibration, we will be able to use geometric parallaxes measured by Gaia for the near environment for several kiloparsecs around us, and then use photogeometric parallaxes from LSST for mapping the more faraway distances. So we will have a good map in all the ranges from like really close to us to the edges of the halo. Well, maybe edges of the halo is too optimistic, but still pretty far away. So how it looks in practice? Well, everyone probably once again heard here about Gaia, which is an excellent space-based telescope for primarily astrometry. But apart from astrometric measurements, Gaia bears on board also a number of other instruments, including two spectrographs that are measuring, obtaining low-resolution spectra with varying resolution in the range from about 330 nanometers and to 1050, traditional cutoff edge. And the resolution is variable, but after some calibrations, what is produced by the Gaia consortium is a single smooth low-resolution spectra that is ranging all the edge, and these spectra are available for over 200 million of sources, which is quite a lot, with magnitude as bright as 17.5, I believe, or something like that. So it is a large sample, good enough for any kind of calibrations that we might need. Obviously, we can produce synthetic magnitudes from the spectra pretty easily. We just convolve it with throughputs from some photometric system. We calculate integrated flux, we convert it to magnitude, so everything is good. You just need the spectra and you need the photometric system bandpasses. But the issue is that actually there are some known biases for these low resolution spectra, and correcting those biases isn't as straightforward as one would think. So first of all, by default, these spectra are stored in continuous form, which is essentially a set of coefficients, which has to be multiplied with basis functions. There are like 550 of them, I think. And this linear combination of basis functions is used to produce a continuous form of spectra. From this spectra, the Gaia XP package that is produced once again by Gaia consortium can be used to produce synthetic magnitudes in a number of photometric systems. The thing is that with systematics that are detected but not corrected in Gaia XP spectra, we have to correct them somehow. And this on the plot, you can see how it is done by the Gaia consortium. So on the left column, you can see uncorrected, you can see synthetic magnitudes for SDSS for uncorrected spectra. And you can see that there is magnitude-dependent bias for the faint sources, which is called hockey stick, which is usually attributed to the not perfect calibration and not perfect removal of the dark flat values. And there is a way to correct for this by, but how it's usually done is by tweaking the bandpasses functions. So not the spectra itself, but the bandpasses of, for example, SDSS or LSST. And these bandpasses are tweaked so that when comparing the synthetic magnitudes against a set of calibration stars measured with high precision, these biases were removed. So on the right side, you can see the results of these synthetic magnitudes after the removal of these biases. So there are some overcorrections, but generally it behaves pretty nicely. So the median residual between the synthetic and observed magnitudes becomes close to 0. Yet we cannot do this in order to produce synthetic magnitudes for LSST, because in order to tweak the bandpasses, we need to compare the synthetic magnitudes with observed magnitudes in the same photometric system. And obviously, we don't have the observed magnitudes for LSST yet. So what we want to do is to use this comparison of the observed magnitudes in some trusted survey, and we are going to use SDSS Stripe 82 survey, which is photometrically quite precise. We want to compare synthetic magnitudes in one photometric system with observed magnitudes in the same photometric system, calculate the residual, use this information to correct the spectra, and then from this corrected spectra produce synthetic magnitudes in the LSST system, which is a bit convoluted when I'm just talking it through. And actually, when I'm writing it down in a paper, it also sounds a little bit convoluted, but I hope that you can follow what is going on here. And this correction has to correct this color and magnitude dependent biases, which are pretty tricky because they are caused by different causes. So first one, there is a hockey stick, which is imperfect calibration. But there are also some noisy regions that appear after this conversion from the continuous form in which the spectra originally stored in Gaia archive. When this continuous form is being corrected to the classical sampled form, so just the dependence of flux from wavelengths, the calibration procedure increases random noises in certain that are pretty strong in certain parts. For example, in the U-band, which is notoriously noisy, it produces wiggles that are going completely crazy. And there is also another problematic region where essentially the wavelength regions between two spectrometers are overlapping. So there is also a noisy part in there. So there are some random noise regions that are pretty hard to correct with anything, essentially. There is also another issue is that a Gaia XP spectra does not cover the full wavelength range of the LSST filters or SDSS filters, actually, because they are pretty close in the range. So there are some issues that have to be fixed. And unlike Gaia consortium that can allow themselves to tweak the filters because they have the real observed photometry to compare it with the synthetic one, we have to tweak the spectra itself. So what do we do to deal with these systematic issues? Well, first of all, in order to fix this issue with incomplete wavelength coverage of the spectra of the LSST and SDSS wavelength range, we have to extend the spectra. For this, we're using synthetic stellar atmospheres models produced by Kurz, so it's pretty famous Kurz catalog. We are using the Gaia stellar parameters to find the best model. We are matching this model, so we are adjusting it a little bit to account for the reddening and for the distances. And then we are essentially extending the observed spectra with synthetic parts. And considering that we have these highly noisy parts in the edges of the spectra, sometimes we even cut completely these noisy parts and replace them with synthetic ones. I will tell about this a little more on the next slide. After this, we want to perform the actual core and magnitude dependent correction. And we tried a number of things, including some pretty smart approaches with machine learning and producing a correction curve with a sum of some basis functions, so pretty similar to what is done by the Gaia consortium. Because we hope that to produce a kind of perfectly corrected spectra that would be corrected exactly in the parts that are causing the biggest issue, this noisy part. So after quite a long period of experiments, we figured out that actually for correcting magnitude and core dependent biases, these approaches do not work very well because in principle, you can produce any number of correction curves with either machine learning or basis functions. And these correction curves, to find the best one, it's first of all computationally complicated. And secondly, there is a question of what would be the criteria to optimize if we want to have actually smooth and nice corrections that wouldn't create any crazy wiggles artificially with this correction. So the approach that actually worked the best was pretty simple. We put all the available spectra on the magnitude grid. So essentially, we are plotting the magnitude in Gaia Max terms. We are putting each spectra in its corresponding cell. We are calculating the median residual per cell for each band. So we have 5 SDSS bands. So this is 5 correction coefficients. And using pretty simple equation, we are calculating the correction coefficient for the magnitude, for the fluxes, it doesn't matter, from this median residual. So we are getting 5 correction planes where each magnitude, where each source has a coordinate on this plane, and from this coordinate, the 5 correction coefficients are determined. So just to illustrate how it looks like, the first step, the extension of the spectra. In blue is the original spectra, and you can see that there are some crazy noises in the U band and sometimes in Z band. They are as crazy that sometimes there are strongly negative flux values, which causes all kinds of problems, and it's definitely unphysical. So it's been actually analyzed and proven that this is instrumental noise. This is not measurement errors. So in order to deal with it, we are essentially just cutting off this part of the spectra and replacing it with synthetic one, with Kurz model. And the cutoff value, we tried several values. So first one is just extending the spectra without removing any of the observed data. The second one is moderate cutoff. So it's, I think, like 350 nanometers. So everything below that is cut off and replaced with synthetic spectra. But actually, the best result for the U-band is just to cut off everything below 400 nanometers and essentially completely replace the U-band with synthetic one. So it is better to use synthetic models for the U-band than use actual observations. For Z-band, we can cut off just a little bit of the Z-band and it works fine. And this is this extended spectra before and after the correction. So in blue is before the correction, and in orange is after multiplying by these correction coefficients. So you can see that the difference isn't so that strong. But if we would try to use one of the smartest approaches that would look for correcting specifically more problematic areas, sometimes there would be some crazy spikes that are simply unphysical. And we couldn't figure out how to deal with this issue without using more high quality spectra, which could have been done, and maybe we will do this in the future. But for the purposes of our tasks, for obtaining synthetic photometry, it turned out to be easier and much more precise to just use this sort of inelegant but working approach with just correction on the magnitude grid. So what about the results? This is the same plots that I showed earlier, but already for our correction. And in the left column, you can see residuals between synthetic and observed SDSS magnitudes for the U and G band for the uncorrected spectrum. So you can see that there is a pretty noticeable median shift. So pay attention that U band is in different scales than G and grids bands below, because U band residuals are much larger. So there is a pretty noticeable median, and there is this hockey stick effect that we talked about. In the middle column is the synthetic magnitudes residual produced by the Gaia XP package, so by the Gaia consortium, with these corrected, tweaked band passes. So you can see that the median is much smaller, and the hockey stick effect is seriously compensated for. But with our approach, we are getting actually even better results. The median shift is going to effectively zero, and the hockey stick effect is almost unobservable. And if we look at the same residuals depending from the Gaia cores, we can also see that there are really strong biases for different bands that are corrected in a good way by the Gaia consortium, but corrected even better by our brute force approach. So for the rest of the bands, it is not so evident, but it is still pretty obvious that yes, there is this magnitude and color dependent biases that you will see below that are very well corrected with our method on this magnitude correction plane, let's say. So yeah, color dependent stuff is actually much more evident for the U and G band. This is why they're more illustrative. But something that we can also have a look at is the bin statistic from the magnitudes or from the core. And if for the U band, the correction of this brute force correction of the spectra itself is pretty much on the same level as the correction with tweaking the spectra, at least in terms of median residual. Then for the grids bands, the correction using correcting the spectra with this grid approach is actually performing much better. Which is quite nice for our purposes. Although on the downside, of course, well, this correction is imperfect and quite crude. So we are effectively tweaking the whole parts of the spectra corresponding to the whole wavelengths of separate bands. So it is a crude way to do this. I wouldn't use those spectra for any kind of precise science that requires seeing how, well, for example, any kinds of spectral lines. Yeah, those correction isn't going to work for this. And just to show you how these correction planes are looking, so most of the objects are concentrated along this stripe in the magnitude coordinates. And the median residuals are pretty smoothly distributed for grids bands, although there is this region of serious change in the correction coefficient for the U band. This is the only problematic region, and we attribute it to the highly noisy sources for the highly noisy faint sources, because this is actually for the large magnitudes. for the reads bands, the transition between different coefficients is really smooth, which is pretty nice, which is pretty physical, actually. So as a result, what we are getting after this correction, we produced the catalog of synthetic magnitudes for the Stripe, for the SDSS photometric system, because we already did this correction, and also for the LSST system, which was the original purpose. And this correction procedure is in general applicable to calibrating against other surveys. So something that we are doing now, we are checking whether we can get better results with using observed calibration magnitudes, not from Stripe 82, but from DES survey, dark energy survey, because it has pipelines, scientific pipelines that are closer to the future LSST pipelines than Stripe 82. So it might be better in terms of the future closeness of the calibration with the LSST. Trying to calibrate to use this kind of stuff for producing synthetic magnitudes for other spectral datasets is also something to look into, although we are not sure that we are going to do this. What is probably more interesting is to try to do this calibration with the data preview photometric data that LSST is going to produce in several months. And depending on how well this correction procedure will show itself in terms of comparison between the calibration against Stripe 82 and calibration against LSST data preview data, we can either use the data preview data for better calibration, and then these synthetic magnitudes will be as close to actual LSST magnitudes as possible. And then we can use jointly the Gaia XP dataset together with photometric dataset from LSST. Or if there will be some differences noticed, well, then at least we will know how to take into account them when we are making our distance ladder, for example, distance ladder calibration by when we join different data sets, the ones that are applicable in the nearby environment near the Earth, and for the stars that are more far away. So these are several applications that we are going to probably try on in the next year or so. But other than that, the methodology is developed, and that catalog isn't publicly available yet because we are still setting up the data access system, but it is going to be made available probably by the time when we are finishing with the draft of the paper and send it for publication. So this is it for now. And I hope I didn't speak too fast and I didn't go out of time. This is 3 at my time, so it's 4 at yours. And thank you. Your questions.
Thank you very much, Alexandra. Please, questions.
I have one.
Please.
Yep.
Thank you. Sasha, about solar system, possible new discoveries of new asteroids with LSST. I looked at that slide that you promise to find 5 million new asteroids with LSST. Too much estimation. Where you are going to find new 5 million asteroids?
So I don't think I have to check so because I don't want to lie, but I think that we are talking about observing 5 millions of asteroids, not actually discovering millions of new ones.
Okay.
Yes. This is probably incorrect statement on my part. I know that there are promises of great volumes of new asteroids found in terms of trans-Neptunian objects, for example, because this is distance objects that are not. Yes, but for the main belt asteroids, I think it is an observational estimate, not discovery one.
Okay, and one more justification. That is, LSST will observe the same area twice per night. Is it true?
No, one time every 3 nights.
One time.
So every 3 nights it will sweep the whole southern sky. Approximately, because the real schedule of observations, it is not determined yet. So some parts of the skies will be observed more often, but on average, this is the estimate.
Okay, but maybe I can't catch. In some slide, I found the 15 minutes gap between.
Yes. Yes. So
15 by 15.
Yes, so this is a bit related to how the observation is done. So every visit of every patch of sky, so when LSST is observing, it will do 2 exposures, each by 15 seconds, one after another. Yes, so for the differential analysis, so that if you want to detect the moving objects, you will observe the patch of the sky now, look somewhere else, and then in some minutes you will look at the same part of the sky again, measure, so this, do the differential analysis, one image subtracted from another, and this difference is for producing alerts. Yes.
And then return back to that patch after 3 nights.
Approximately, yes, because the exact, yes.
Okay. Thank you.
I have small questions, not directly connected with theme of your talk, but close to the LSST. We know that many photometric surveys have problem with galactic plane because the high density, stars density.
Yes.
And what is the solution in LSST?
The solution is horrible. I mean, horrible not in terms that it's horrible, like ineffective, but horrible in terms that it's very complicated. It is indeed a serious issue because for LSST, for its depth, for its resolution, actually observing galactic plane is a nightmare because there is essentially no unblended patches of the sky. So if you look at most of the objects, they are going to be overlapped with something else. So the solution they are going to do now, there is a whole subgroup that is working on this, is obviously an attempt of some kind of probabilistic analysis. So they are going to produce sort of a maps that are evaluating how probable is that this pixel belongs to this object or doesn't belong. I'm not going to go into details because I do not know them, but I know that there is no other way. So you cannot clearly separate the objects with this depth and with this resolution for the galactic plane. It's just like physically impossible. You are observing too much.
Thank you.
Okay, can I ask a question too?
No?
So thank you very much for the nice talk. And of course, my question, I could see that you represent from the set of the tasks which LSST will do, also unified scheme, the checking of unified scheme or genes. Of course, I have a question, but how? As I understand, yes, you said about variability.
Yep.
But maybe you can tell something a little in detail. What is plans, and also and also the second question. Probably I didn't hear it by mistake. Probably you said about this. What about gravitational waves? Because I think it will be used for this, of course, as an important telescope. So just these 2 questions.
So I will start with the second one because it is easier. So yes, LSST has target of opportunity program, and the alerts released by the gravitational wave observatories, they are going to be used for rapid retargeting of LSST and for observing the optical counterparts. I think that this program is actually a little bit underdeveloped, so it definitely exists, but there is no clear strategy how it is going to be done. So I believe that at least for the first year or 2, it's probably going to be very uncertain in terms of probably it's going to be done on the level of personal communication between the networks, unfortunately.
Okay.
But in the future, so there is in general a talk about creating large coordination systems between different observational facilities that would be automatically retargeting a lot of telescopes to look at the patches of the sky. Well, in some degree, it already exists. But right now, there is no common protocol that would coordinate the observations of the targets of opportunities as soon as alert is produced. There is work in this direction. LSST is going to be part of this inevitably. So this is like the generic answer that I can give, because in details you would have to talk to someone who's actually working on this. As for AGNs, it is much more complicated question, and I'm probably not qualified to properly answer this. But yes, so variability right now, unified model is a bit, so depending on whom you are going to ask. Some people are actually claiming that it doesn't explain most of the observations that we are having now. And there is a talk about several types of agents that can be followed several unified schemes. But what is mostly interesting in terms of what LSST can help is change in state AGNs that maybe show some light about why we have different subtypes of AGNs still, even within the unified model. So since LSST is going to observe each patch of the sky with a high cadence, we can, and since it's going to be pretty sensitive and observe billions of galaxies, we can catch a lot of AGNs that are in these rapidly changing stages of their evolution. And the hope is that if we have a large sample of these AGNs, we will get more information about why we have these discrepancies between observations and theories. Once again, I'm not an expert in this, so I'm the wrong person to go into details, but I take that this is the main hope, that we are going to have a larger sample of change in state AGNs and that it will shed more light into the unified model.
You mean the changing of the type 1 to type 2, like this,
Yes,
middle between
yes,
them,
yes.
to understand what's happened exactly, why
Yes,
they are changing the type?
yes, mainly, but also the AGNs that are showing, so there are several, I'm not sure how exactly what is the size of the sample of these objects, but I think it's maybe dozens or maybe hundreds, but not much. The sample of AGNs that demonstrated one behavior some times ago, several years ago, and after repeated observations are demonstrating different properties. So obviously the hope is that LSST with 10-year observational span and this high cadence will be able to sample these types of objects quite regularly, and that we will understand what is going on with them.
Okay, probably we will hope to understand much more about this, yes. And I'm sorry, just the final questions. I understand it's time. Just about Hubble tension, what you can say about this? So I understand that LSST, there are a lot of problems which LSST probably will solve like this. But of course, about Hubble tension, everybody now speak and what you suspect.
Well, I don't quite believe that I can say anything smarter than you can say. It's me who should be asking you, I would say. So I don't think, the effort in this regard is mostly LSST plus Euclid, because LSST alone isn't the most powerful tool for cosmology, because obviously to observe larger distances, you need infrared. LSST doesn't have this. There is, once again, dedicated group LSST plus Euclid. It's mostly grassroots initiatives between the specialists within both networks. And the joint analysis, well, something that I understand, something that I know from my PhD times, is that they are expecting to have a better quality photometric redshift for galaxies, which is obviously one of the distance ladders for it. Yes. But whether, if you're asking me whether we are going to decide whether Hubble tension is real or not, I hope I hope it's real. Otherwise, it's
You
boring.
hope that it's real, but this is a
Of course.
problem.
But it means that we have something to start. Come on, you know I.
Yeah, it's interesting, of course, but okay. Probably.
I hope we are going to be very bewildered by what we will see.
Probably. It's interesting way because sometimes they could find the paper which says it, you know, it's only technical problem. Sometimes no. So now this is a really discussion of this. Thank you, Sasha.
Well, I hope it's not a technical problem. I realize the chances are that it is because the precision of the analysis in all this cosmology. I mean, I'm not a specialist, but when I listen to the talks, I'm like, damn, guys, you are really, I mean, what kind of strength of character you need to do this kind of precision analysis with these tiny differences. It's amazing. But yeah, I hope that this tension is real. I hope that it's not a technical downsides of our methods. I hope that we will find something really crazy.
Okay, probably. Thank you.
Hopefully.
Young people, you know, they would like to find something crazy.
Wouldn't you like to find something crazy in you?
Yes, of course, too. I also a young person, so
yes,
why not?
Yes, precisely.
Okay.
May I ask small question?
Absolutely.
Thank you, Sasha, for your talk. It's very pleasant to see your expertise, motivation, results. It's really very pleasant. I have a small question about Gaia spectra. We use Gaia spectra for asteroid study, and we just not taking into account blue and red parts.
Yeah,
What you comment? It's for science purposes, we can use also artificial spectra.
So I feel that I am not sure about how you use those spectra for asteroids, because obviously we were working exclusively with stars and we were selecting the star sample. Can you tell a little bit more how exactly you are using this spectra? What are you determining from them? Physical parameters?
Sometimes it's just colors to compare with color classification from another sources.
Okay. Well, you definitely cannot use the synthetic models that we are using because they are for stars. And if you need something for asteroids, I'm not sure whether there are synthetic spectral models for asteroids. I believe they should exist, but whether they are good enough and whether the database is large enough. So I think that probably this method won't work for you, unfortunately, but I have to think about it.
Thank you.
Because obviously, well, if you want to use some kind of synthetic data, you have to have it. So I'm not aware whether there is something suitable for the asteroids.
Yeah, I understand. Thank you.
Any other questions from audience? If not, thank you very much, Alexandra, for your talk, for discussion and for answering our questions. And we wait.
Thank you.
Your new talk.
Thanks a lot. We hope to see you again and again, and then dream about meeting somewhere in Europe.
Yes, absolutely. I would really hope that we will meet both in Europe and in Ukraine in the next observable future. And yes, I would very hope for this. Well, in any case, I mean, I am always happy to see any of you around our places. So if you are going to be around Croatia or Slovenia for any purposes, please drop by and say hi, and we will chat the science in person. And maybe we will somehow one day organize something even around your parts of the world. Who knows? Hopefully.
Yeah.
Vadim Grigorьевич